I'm Quiles.
I'm Logan, Pawlowski.
And our final project is a LiDAR scanning system.
Cue the B-roll.
LiDAR is an acronym for Light Detection and Ranging. LiDAR is an optical technology often cited as a key method for distance sensing for autonomous vehicles. LiDAR works by emitting laser light from a source. Once emitted, the directional object hits objects in the beam's path and is reflected back. The reflected beam is received and processed to measure the time of flight, enabling real-time 3D mapping, object detection, classification, and tracking. Multiple LiDAR sensors can be integrated into the design of any vehicle, providing a 360-degree field of view. However, LiDAR is used in a variety of applications. Labs at the University of Arizona also use LiDAR to create a better model of traffic flow. The School of Anthropology also used LiDAR to reveal the details of ancient Olmec sites in Mexico, finding nearly 500 ancient ceremonial sites in southern Mexico last year. The University of Arizona Natural Resources and Environment Department also explored the benefits of incorporating LiDAR into wildlife habitat models that can be used to provide detailed, three-dimensional landscape information not available from other remote sensing applications. Our system demonstrates how LiDAR is used in autonomous vehicle scanning systems. The purpose of our project is to develop a small-scale LiDAR scanning system in order to educate the public about LiDAR technology and illustrating how some forms of LiDAR are used in practical applications. Our system uses two motors to control two mirrors attached to 3D printed mounts. The mirrors were glued onto the mount surfaces as shown here. A distance measuring sensing unit, or DMSU, consisting of a detector and infrared LED, was aligned perpendicular to the mirrors such that the infrared LED could travel between the mirrors and onto an arbitrary scene. The backscattered reflection from the IR LED returns a particular voltage to the detector based on its distance traveled. This makes sense based on the theorem of radiative transfer, for as the distance z increases, the irradiance on the detector will also decrease.
By experimenting with the DMSU's distance versus voltage relationship, we were able to map the returned voltages to a specific distance. These mapped distances could then be used to generate a graph of all returned voltages called a point cloud. The feed has to be continually updated live to generate a real-time point cloud just like an autonomous vehicle, but the Arduino IDE does not have this capability. To do so, we wrote motor controls and point cloud graphing within MATLAB by finding a way to interface MATLAB with an Arduino. We then coded the motors such that the rotational motion of the mirrors produced a linear raster scan with the IR LED. We also aligned a laser diode with the IR LED that can be turned on and off visually to illustrate the light's path. On top of all of this, we have also included a joystick the user can manipulate to directly control the motors and scan any part of the scene.
We were fully responsible for the 3D modeling and printing of the system, the electrical wiring for all components, the coding, and integration of all disciplines to create a fully functional small-scale LiDAR scanning system, which is a widely used optical technology across the globe. The basic principle related to the theme is how light detection is used in practical applications. Our project clearly shows how the interdisciplinary skills of mechanical design, electrical engineering, and software engineering combine to create cutting-edge technology that drive innovation.